Whoa! Whoa! We're diving in. This is like the 6th reading of modern refrigeration and air conditioning. Little bits and pieces. That's what's going to get me the most billions in the bank by age 60. By doing little bits and pieces like this. Okay, here we go. We're reading. Fixtures may be installed in the ductwork if heavy contamination exists there. Lamps should remove 80 to 90% of the bacteria in domestic and commercial systems. They should remove at least 99% in hospital operating and recovery rooms. Systems that remove more than 99% of the bacteria are more expensive, but may be required in some applications. Since these lamps are stronger than their commercial and residential counterparts, no human exposure to the light they generate can be permitted. The useful life of a lamp varies with output, but may be as high as 9,000 hours. Indoor air quality systems. In the past, a natural exchange of air through infiltration, leakage of air into a building, and exfiltration, air leaving a building through doors, windows, and other construction joints, was presumed satisfactory. Additional exchange of air was provided by the opening of doors and windows. Today, systems that provide ventilation and increase air quality are recommended due to the increasingly tight envelope, increased insulation and sealing of newer home construction. An important responsibility of a residential home's HVAC system is maintaining the quality of the air. Some residential homes are equipped with complete indoor air quality systems. An indoor air quality system is a controlled ventilation system that exhausts stale, humid air and reduces pollen, dust, odors, and other pollutants. A complete system consists of numerous components, including an air conditioner, high-efficiency variable-speed furnace, humidifier, air purification system, UV germicidal light, and a heat recovery ventilator, HRV, or energy recovery ventilator, ERV. The components in this type of system are coordinated to ensure adequate ventilation, heating, and cooling. To maintain indoor air quality, stale indoor air is exchanged with fresh outdoor air. However, while outdoor air may be fresh, it is often not at the same temperature and humidity as the conditioned indoor air. To reduce the energy loss that would be required to recondition incoming fresh air, HVAC systems route incoming fresh air through an HRV or an ERV. Heat recovery ventilators, HRVs, and energy recovery ventilators, ERVs, deliver fresh air into a home's interior and improve ventilation. A heat recovery ventilator, HRV, is a heat exchanger that passes incoming fresh air and outgoing stale air through a series of parallel passages. As each airstream passes through the HRV, heat is exchanged, so the incoming air is closer to the temperature of the outgoing air. An energy recovery ventilator, ERV, is constructed and operates in the same manner as an HRV. However, an additional component allows ERVs to transfer heat and also humidity. ERVs and HRVs are mechanical ventilation systems. HRVs/ERVs are referred to as balanced systems. An HRV recovers some of the heat that would otherwise have been exhausted. Through the use of fans, HRVs/ERVs provide a flow of fresh outdoor air into, and that's it. I'm not going to read. I said just do one page, even if it leaves us on a cliffhanger. Okay, this looks technical. Are treated as a single entity. In other cases, the type and thickness of each material in the component are considered separately. The second step in calculating how much heat is leaking is to determine the rate at which heat transfers through the various materials. These values have been determined by building material manufacturers under laboratory conditions and are expressed as C values, K values, U values, and R value or R values. These values can be looked up in charts and will be discussed in greater detail in the sections that follow. The formulas used to calculate heat leakage vary slightly depending on which of these values is used for the calculation. After determining the types of materials through which heat is leaking and the rate at which heat is transferred through those materials, the third step is to determine the surface area of each type of material. The greater the surface area, the more heat will leak through the material over a given period of time. The fourth step is to determine the temperature difference between the inside surface of the material and the outside surface. The rate that heat is transferred through a material is directly proportional to the temperature difference between the two sides of the material. With the preliminary data collected, the total amount of heat that leaks through the material in a 1-hour period can be calculated. The formula used to calculate heat leakage varies slightly, depending on whether the materials, C values, K values, U values, or R values are used in the calculation. However, all of the formulas for calculating heat leakage require that the technician know the types, and in some cases the thicknesses of materials through which heat is leaking, the surface area of those materials, and the temperature difference from one side of the material to the other. Thermal conductivity, K value, and thermal conductance, C value. A material's thermal conductivity, or K value, is a measure of the amount of heat that will pass through 1 square foot of the material 1 inch thick in 1 hour. When there is a 1 degree Fahrenheit temperature difference between the two sides of the material, the units used with the K values are BTUs times inch over hours times feet squared times degrees Fahrenheit. Materials used with high K values transfer heat at a greater rate than those with low K values. A K value is typically used to determine the thermal conductivity of a homogeneous material like insulation, drywall, wood, or glass. When calculating the heat transfer through a composite building component like a framed wall or a foam core door, the K values for the individual materials in the component are divided by the thickness of their respective materials. This calculation yields the thermal conductance, C value, of individual materials. A material's thermal conductance, or C value, is a measure of the amount of heat that will pass through 1 square foot of the component in 1 hour when there is a temperature difference of 1 degree Fahrenheit between one side of the component and the other. Notice that the thermal conductance is not based on a 1-inch thickness, but describes the thermal properties of the material based on its measured thickness. In most cases, a material's C value can be looked up on a chart. In some cases, the technician may need to calculate the material's C value based on the K value and the thickness of the material. Thermal resistance, R value. The thermal resistance, also known as the R value of a material or building component, is a measure of its resistance to heat transfer. The R value of a homogeneous material is the reciprocal of the material's K value multiplied by the thickness of the material. A reciprocal of a number is 1 divided by that number. Formula for calculating thermal resistance, R value, using a K value. And then, it shows you little formulas. Building materials have been tested to determine the rate at which they will transfer heat. A material's thermal resistance can also be described as a reciprocal. Those values are recorded in numerous charts which can be referenced when performing load calculations. These charts usually list the thermal resistance of materials and common building components. Occasionally, a technician will need to calculate the resistance of not reading anymore. It's the second page. Okay. Interlocks and access panels. A safety interlock switch is often provided inside a furnace's blower access door panel. When the door or panel is opened or removed, this switch turns off electrical power to all components and eliminates the possibility of personal injury due to moving parts. Two-stage furnace. A standard furnace has only one heat level, high. It waits until the temperature in the conditioned space drops, then it starts up and runs at one constant output when it receives a call for heat. A two-stage furnace can produce two different levels of heat, allowing it to adjust heat output to meet demand. The flame can be on high, low, or off. When less heat is required, a two-stage furnace operates on the first stage, which uses a lower percentage of its capacity to produce sufficient heat. This stage consumes less energy, thereby increasing efficiency and cost effectiveness. In addition, two-stage furnaces are much quieter than single-stage furnaces. On colder days, the furnace functions on the second stage to provide high heat. This allows the unit to meet the demands for more extreme temperatures. The blower motor speed increases when the furnace switches to the second stage. By producing more or less heat for a given amount of time, a two-stage furnace adjusts to changing heat loads. This adaptability helps to maintain a consistent temperature in the conditioned area by reducing the temperature fluctuation caused by excessive heat being distributed too quickly. In addition, the blower fan slowly increases or decreases speed during startup and shutdown, eliminating the sound of rushing air as it enters or exits ducts. Variable speed blower motors. Variable speed blower motors adjust speed to automatically to meet the temperature requirement set on the thermostat, creating a more comfortable environment and increasing efficiency. They also keep air circulating at low speed between cycles, thereby limiting energy waste significantly. The consistent airflow also allows the air filter to trap more pollutants, providing better indoor air quality. Modulating furnace. In modulating furnaces, solid-state integrated controls act as the brain of the furnace. Some modulating units can vary their heat output from 40% to 100% of their total capacity. After receiving a call for heat from the thermostat, the controls initiate and manage a sequence of events, directing the furnace so that it supplies heat to the building efficiently. Some furnaces can automatically choose the most efficient indoor blower speed when continuous air circulation is desired. An induced draft combustion blower quietly provides air for combustion and vents the products of the combustion from the heat exchanger to the outdoors. Forced air duct arrangements. As discussed earlier in this chapter, a forced air heating system uses a motor-driven blower called an indoor blower to circulate heated air. With this heating arrangement, a system of ducts, referred to as supply air ducts, delivers warm air into the conditioned spaces. Another system of ducts, referred to as return air ducts, brings air back to the furnace for reheating. Both supply and return air ducts are carefully sized to provide the correct amount of airflow to each room. Forced air duct systems usually include an air filter in the return airflow to the furnace. A humidifier is often installed in the supply airflow to provide the proper relative humidity conditions. The duct system may also include numerous dampers, grills, and diffusers. To review these components or for information about duct sizing, Makeup air units. Negative pressure problems are often caused by forced air heating systems, which require oxygen and fresh air for combustion in the furnace. In a home that is sealed and insulated well, the furnace's need for fresh air results in a negative pressure developing inside the house. Rather than allowing this negative pressure to cause infiltration around doors, windows, or wherever an unintended opening may be, technicians can install makeup air units. Makeup air units are devices that control and regulate the necessary intake of fresh air into a building. Current codes and regulations in many states require the use of makeup air units to prevent negative pressure from developing in a house. In single-family residencies, makeup air units are usually automatic, passive devices with few controls. Makeup air units for larger installations and commercial applications are often automatic, active devices with more controls. Although variety exists in manufacturing, there are two common places where makeup air is deposited in a building: directly into the return air duct or into the furnace room. Okay, 15 minutes this time. That's longer than usual. Thanks for tuning in. I will see you soon.